Hey guys, welcome to the next video on OpenCV tutorial for beginners using Python. In the last video, we have seen a brief theory introduction about Hough Line Transform. So I have told you that OpenCV implements two kind of Hough Line Transforms. One is a standard Hough Line Transform using HoughLinesP method, and the second is the probabilistic Hough Line Transform using HoughLines capital P method. So we are going to use the Hough line method in this video and see how we can use this Hough line method to detect the lines inside an image using Hough transform. Now I also told you that there are 4 steps associated with Hough transform. So the first step was the edge detection step using any edge detection method, preferably Kenny edge detection. The second step is the mapping of edge points to the Hough space and store these edge points to an accumulator. The third step was the interpretation of accumulator to yield lines of infinite length, and the fourth step was the conversion of these lines to the finite lines. So let's say we have this image of this sudoku.png, and you can see all these lines here which we want to detect. So this is the line and this is the line. So all these lines we want to detect using the Hough line transform. So I have already written this code, so I'm going to go step by step to explain how this code works. So in the first step, you just need to import the normal cv2 and the numpy as np. Then here I'm just reading this image using imRead method. In the next step, I'm converting this image into a grayscale image and storing it into this variable which is gray, because for Kenny edge detection it's preferred to have grayscale images rather than your normal colored images. Now in the next step, we are applying the Kenny edge detection method on this grayscale image. So here this cv2.kenny method takes these arguments. First argument is the image, second and third argument is the first threshold and the second threshold. So I'm giving the first threshold as 50 and the second threshold here as 150, and the fourth argument here I'm giving aperture size is equal to 3. Now in the next step, I'm using this HoughLines method. This is the normal Hough transform method which is implemented in OpenCV. Now this Hough line method takes few arguments. The first argument is the image. So we are just passing this edge detected image to the first argument of this HoughLines method. The second argument here is the row value. This row value is the distance resolution of the accumulator in pixels. Normally it's taken as 1. The third value is the theta value, which is the angle resolution of accumulator in radians. So for that we are just using numpy. So np.pi divided by 180. So this is also typical in this method. And the next argument here is the accumulator threshold parameter. So what does this mean? It's a threshold, so only those lines are returned that get enough vote. That means that those lines will be returned which have threshold greater than this value. So starting value I have taken here as 200 as threshold. So now this HoughLines method is going to return the output vector of lines. Now I have explained you how polar coordinate works for the Hough transform in the last video. So these lines will be in the polar coordinate. So each line is represented by 2 or 3 element vectors, either rho and theta or rho, theta and votes. So as you can see, this is the output vector of lines. So I'm going to iterate over each and every line vector, and what it gives is the first element of this line is going to give you these two values, rho comma theta. It's going to give you rho comma theta or rho comma theta comma volt, right? So right now I'm using just two parameters here, rho comma theta. So rho is the distance from the coordinate 0 comma 0, which is the top left corner of the image, and the theta is the line rotation angle in radians. So all this rho and theta I have explained you in the last video, and we have seen how we can represent these rho and theta values in the Hough space. So first of all, what we are going to do is, once we get the rho and theta value, is we are going to just get the cos theta value and the sin theta value, because we want to convert these polar coordinates into the normal Cartesian coordinates for the line method, because this line method, as you can imagine, takes these coordinates, right, which are the Cartesian coordinates. So this is the 0.1 parameter and this is the 0.2 parameter, so x1 y1 and x2 y2. So first of all, we are just getting the cos theta value, and theta here is this theta. So cos theta we are just assigning to A, and the sin theta value we are just assigning to B, and we are just multiplying this A to the rho. So this will give us the x0 value and the y0 value when you multiply B by rho. So this rho is this rho value. So this x0 and y0 is going to give you the origin, which is 0 comma 0 or top left corner of the image. But we want the lines, not the top left corner of the image. So how we can get these x1 and y1 coordinate and x2 and y2 coordinate? This is given in this equation. So once you get your x0 and y0 value, you can get the value of x1 and y1 coordinate using this equation. So you just need to typecast everything into integer. So this equation, x1 value stores the rounded off value of rho, as I have shown here. So this r represent rho. So rho multiplied by cos theta. Cos theta we have already taken in the a variable. So we are essentially here multiplying the rho multiplied by cos theta minus 1000 multiplied by sin theta. Sin theta value is the value of the b, right? So x0 plus 1000 multiplied by minus b here. Okay, y1 we get using this equation. So y1 is equal to int in the bracket y0 plus 1000 multiplied by a, which is essentially this equation, which is rho multiplied by sin theta plus 1000 multiplied by cos theta. So these two values are going to give you the first coordinates, and similarly we are going to get the x2 and y2 coordinate using these two equations. So here everything is same, just this minus is new, right? So in this equation you just need to replace a plus by minus and you get the x2 value. Same you have to do in the case of y2. So in this equation, if you just replace this plus by minus, you will get the y2 value. And we have already seen how to use the cv.HoughLine method. It takes a few arguments, as you can see here. First is the image. So image is our original image. Second is the x1 and y1 coordinate, which is the first point, comma the second point. So as you already know that a line is a collection of points, so you need at least 2 points to create a line, right? So this is the coordinates of the first point and this is the coordinates of the second point. The next argument here is the color. So color I have taken simply 0, 0, 255, and the last parameter here is the thickness of the line, which I have taken 2 here. And the next line of code you already know, I think. So after this line we come out of the loop and we are just plotting all the lines using this loop on the original image. And once we get all these lines on the original image, we are just showing it using IMShow method, and at the last we are just destroying our window once we are done with the image. So let's run this code and let's see what happens. So I'm going to run this code, and you can see all these lines are plotted here. Let's see the Kenny edge detected image also. So I'm going to just after the Kenny edge detection, I'm going to once again add this IMShow method to show the Kenny edge detected image also. So you can see here, this is the Kenny edge detected image. All the edges are detected, and based upon all these lines which are detected here, these lines are drawn. But the problem here is these lines are of infinite length, so there is no end to these lines. These lines just go from the start or the corner of the image to the other corner of the image. So you can see they start from here and go to the next corner. They don't just stop here. So in this Hough transform, you see that even for the line with 2 arguments, it takes a lot of computation and we don't even get the correct result. So this problem can be solved using the other method, which is implemented using this HoughLineP method, which is the probabilistic Hough Line Transform, which I'm going to show you in the next video. So how we can get the better result using HoughLineP method, we are going to see in the next video. So we are going to apply the HoughLineP method on the same image and we will compare the result. So that's it for this video. I'm going to see you in the next video.